In this problem, we will graph f of x equals -2 times the absolute value of x minus 3 plus 4 using transformations. To begin with, we need to start by making our list of transformations. So, we'll start with a little chart here. And when you make your list of transformations, the first one that you should do is the parent or base function. So the parent or base function is basically the most simplified form of the function you are given. So if we look at this function and we remove all the clutter, all the numbers from it, the base or parent function would just be the absolute value of x. This function takes the absolute value of x and performs a bunch of transformations with it. So to graph using transformations, we will start with this parent function and then perform each transformation to it. From here, the next type of transformation that we want to perform is anything that involves multiplication. So we'll look at this function and check what's being multiplied to it. And there's a -2 being multiplied. So we start with the negative and then go to the 2. Multiplying the outside of our function by a negative means that we are performing a vertical reflection. So we'll make a note here. Vertical reflection. So whenever you see that negative on the outside of your function, that's telling you you take the entire graph and flip it vertically over the x-axis. From here, we had that 2. So we've taken care of the negative that we're multiplying by. Now the 2. Whenever you're multiplying by a value between 0 and 1 on the outside of your function, that means you have a vertical shrink or compression. When you're multiplying by a value that is greater than 1, it means that you have a vertical stretch. So in this case, our graph is being multiplied by 2 that's greater than 1, so we have a vertical stretch occurring in this graph. And now from here, the next 2 steps can go in either order, and it's the addition and subtraction that are within the function and on the outside of it. So we'll just start left to right. We have this -3 inside of our absolute value. So whenever you have a minus inside of your function, that means you're going to shift opposite. You're going to shift to the right. So the entire graph gets shifted to the right 3 because of that minus. If it were a plus, then we would shift the entire graph to the left 3. But because it's a minus, we go to the right. Now this 4 that's being added on the outside you go exactly the way you think you would. If it's positive, you go up. If it's negative, you go down. It's not like working with the inside how you go opposites. So this 4 means that we have to take our entire function and shift it up 4 because it's positive. Now that we have all of this information, we can get a rough sketch of our graph. Okay. So it doesn't need to be anything perfect, just a rough idea to show us what this graph will look like. So we start with our base or parent function. That's the absolute value of x. That looks like a v. Okay, and I'm going to make a color code. So I used black for this first one. I'll go ahead and switch to red for the second one. So a vertical reflection means that we're going to take this entire graph and mirror it over the x-axis. So this is the x-axis. Everything above the x-axis will flip below it. Everything below it will flip above it. So this graph will look like this when we flip it below the x-axis. That is our vertical reflection. Now I'll switch to yellow for the vertical stretch. And a vertical stretch literally just means we're going to take every y value and multiply it by whatever number caused the vertical stretch. In essence, we're pulling all of our y values up or down while keeping the x value the same. So for instance, if we consider this point on our red graph now, let's say it just has a y value of -1, and maybe yellow isn't a good choice here. I'll switch to green, it's a little easier to see. So let's say that this point on our red graph is at y equals -1. Then if we multiply that by 2, it becomes y equals -2. The new point would be here. Same thing if we take this point here at y equals -2, and if we multiply that by 2, we'd get y equals -4. Everything is getting shifted long ways. We're pulling it down. So let me remove these arrows. Okay, so with that, the same thing is going to happen on the other side of the graph as well. These points will get brought down like so. And the only point that'll stay where it is the one directly on the x-axis, because this point represents y equals 0. And 0 times 2 is still 0. So a vertical stretch will look like this. You do not have to show all of these steps. This is just to give you an extra idea of how this works after we cover some examples in class. So our graph literally got longer. If you notice, these y values that were shorter are now further down. They've gotten longer. Okay, so we'll keep going with this. We're nearly done. I'll now switch to purple. So shifting to the right 3 means we're going to take every value on our green graph and shift it right 3. And the way that we show this with a quick sketch is by marking down 3 units and taking our x-intercept, which is right here now. We're moving it 3 units to the right, and we're going to redraw the green graph. We want to redraw it with its stretched out form, so we're not redrawing the red graph. So it's going to look something like this. And finally, our last step, which I will put in brown, is to take this whole graph and shift it up 4. So again, we'll mark 4 off on our graph, on our y-axis this time, and we'll take the x-intercept and shift it up 4, and then redraw the purple graph, like so. And that was pretty poorly done on the second part. It doesn't have to be perfect, but that was pretty terrible. Okay, and now this brown graph represents the final graph. Ignore all of the other colors on this graph. The graph of f of x equals -2 times the absolute value of x minus 3 plus 4 is this brown graph here. This is a rough sketch of it. All of these steps in between were the transformations that led us to this brown graph.